Back again.
Back again, or back for the first time. This is episode 1.
Yeah.
Hello, everyone, and welcome to the Core of Everything, the podcast where we discuss the basics of rocks, geology, how the Earth formed, the rise and fall of dinosaurs, the resources beneath our feet, volcanoes and earthquakes, and so much more, including how geology actually ties into everyday life, like phones and cars and everything like that. So let's kick things off and let's get into the nitty gritty. I'm Jack Turney. I'm a PhD student from Imperial College London, and I look at how resources like fluids and gases move underground under the subsurface. And joining me today is Mark Boyd, another PhD student.
Hello, I'm Mark, and I'm researching micrometeorites, which are little pieces of space dust and other microspherules, little tiny balls of rock in the geologic record, and learning what they can tell us about ancient climates and environments.
Super. And today we're going to bring it right back to basics, and we're going to ask a crucial question, and that is, what is a rock? So, what is a rock? Well, when I tell my friends I do geology, or when they ask me what is geology, I mean, they always just think it's just rocks is a basic definition, and actually they're kind of right, but it's so much more than that. It's, as I said earlier on, it's like how it ties into everyday life. It's resources. It's the computers that we use. A lot of things come from rocks. But I was once asked in an exam, and this sort of spawned this inspiration for this podcast. I was once asked in an exam, what is a rock? And truth be told, I didn't know the answer, which it was 2 marks. And I started things off with a rock is hard.
Strong start.
A strong start, and I got 1 mark for that.
Nice.
And I couldn't elaborate.
That's a generous marker.
Yeah. I know. I don't know how I got it, but I it's never something I really considered before. I just thought, like, a rock is a rock. It's a cliff face or it's a wrestler. I never really thought like, what is a rock? And I had to actually search for it before doing this podcast. I wanted to make absolutely clear that I knew what it was. And from the British Geological Survey, it's considered a rock is a solid collection of minerals.
So the question is, how do we get this collection? So minerals accumulate as they are pushed together when they're buried in the earth. So they can be pressurized by plate tectonics, which are just large slabs of the Earth's crust, the surface, or they can be cemented together by fluids underground, or crystallize from cooling magma or lava, so molten rock, whether it's under the ground or above the ground. So it's just an accumulation of minerals.
Exactly. So if a rock's an accumulation of minerals, then the follow-up question, which is absolutely clear as day, is what is a mineral?
Yeah, so a mineral is a material that has a defined chemical composition, so it's composed of one or more elements, and it has a repeating crystal structure. So it's a solid, naturally occurring substance with a regular sort of chemical formula. And when we talk about elements, we're referring to different atoms composed of electrons, neutrons, protons. The atomic number tells us the number of protons. The atomic mass is the protons and neutrons added together. So these are all shown in our periodic table. We've got oxygen, hydrogen, helium, and then more obscure ones like neodymium, dysprosium, lawrencium, things like that. So our elements make up that chemical composition, and they can occur by themselves or as native element minerals. So things like a copper deposit, for example, where you just get copper by itself rather than in an ore. And then that formula then repeats in a regular ordered way to create crystals of that mineral.
Yeah, essentially, if a rock's an accumulation of minerals, but I think you have some rocks like, is it pumice? That's not really, I don't think that's an accumulation of minerals, right?
Yeah, so pumice is made up of ash, which is just glassy material. So the thing about glass is that it's not got a regular repeating chemical formula. Yeah. So I guess by this definition, pumice wouldn't actually be a rock.
Yeah. I guess there's always going to be exceptions to the rules, but on a grand scale, a rock is a collection of minerals. And then you can follow up by saying, if you say that a formula that repeats in a regular ordered way creates crystals of that mineral,
what's a crystal?
It's like, what's a crystal?
Yeah.
Or what's the difference between a mineral and a crystal? And so rocks and crystals are made up of minerals. So a mineral is a solid made of elements that come together in a arranged specific pattern. And these patterns can stack up on top of each other to form a crystal. And if they're arranged in, say, like a hexagonal, rhombic, sort of cuboid arrangement, this gives cool sort of 3D shapes that you see, like amethyst and quartz, that you can like buy in shops and that have I don't know, astrological, like, you know, or what's the term, like meditative properties,
Healing properties.
if you like that stuff.
Yeah.
So if you look at amethyst and quartz, they're composed of SiO2, so silica and oxygen, which are some of the most common elements in the crust. Pyrite's another one, which everyone might knows as being fool's gold.
Yeah.
And that's made of iron and sulfur, and these form large cuboids, cubes. And some minerals contain the same elements and the same chemical formula, but are actually arranged slightly differently, so can form more than one type of crystal. So although they have the same chemical formula, they're actually called different things, and these are called polymorphs, which is derived from the Greek word poly, meaning many, and morph, meaning forms, so many forms.
So our crystal is basically just a manifestation of our mineral.
Yeah, for sure, yeah. So, for example, aragonite and calcite, both calcium carbonate, which compose of limestones like the White Cliffs of Dover. These minerals have the same chemical formula, but actually have slightly different internal structures. And over time, aragonite is unstable and becomes calcite.
Okay, so calcium carbonate kind of that makes up limestones, these calcite, aragonite, has calcium in it. Does that make our bones stronger if we eat it?
Yeah, I mean, I think it would taste pretty disgusting.
Yeah.
It's not quite like a petit falou from your, from the childhood.
Smooth
and creamy.
Yeah.
So from CO2 in the atmosphere, gets dissolved in oceans to form carbonate, which reacts with calcium to form calcium carbonate, which forms the solid shells and skeletons of ocean animals. So oyster shells are made of calcite or aragonite. And actually oysters can use the aragonite to form pearls, which is not a mineral crystal, but is considered a gemstone because of their rarity.
So the same thing is making up shells of our animals that are making up our rocks.
For sure, exactly.
Cool.
Then another polymorph, which is actually quite cool, is a diamond versus graphite, both made of carbon. But the properties are massively different because you wouldn't want an engagement ring made of graphite or a pencil made of diamonds necessarily.
I'd say that'd be a very functional engagement ring, actually.
Yeah, exactly. Yeah.
I need a pencil. Oh, there's one on my finger.
Here's my engagement ring. Yeah, exactly. Or a diamond pencil. You wouldn't be lending your pencil case out that often.
Yeah, true.
And also you'd be ripping the paper and it'd be a nightmare. Anyway, so yeah, you have minerals that accumulate into rocks.
Yeah, manifested.
And that
as
signals
crystals.
the first break.
Ding.
Ding.
So we've spoken about what makes up a rock, but we see rocks everywhere. So can we talk a little bit about the processes that make them and what our types of rocks are?
We certainly can. So there are three main rock types. We have our sedimentary, which is the main most popular, or most common.
Not sure about that.
Yeah, it's the most common anyway.
Okay.
Igneous and metamorphic are the three rock types. And they're all interlinked in this web of processes, which is known as the rock cycle. And let's start with a process known as weathering and erosion. So all rocks are broken down into smaller particles by weathering and erosion. Weathering breaks down the rock and erosion carries the particles away. So this can be by wind that wears down the rocks, like you see weird rock shapes in deserts. Water, which smashes against the rocks in streams or in the sea. And streams are very high energy. So you just look at like the Grand Canyon and that's eroded, small streams have eroded away at the rocks very slowly. I think the National Geographic reported that on average it's less than half a metre every 200 years. So we're talking, a very, very slow level of erosion for the Grand Canyon. And then you've got cold temperatures where water can get into cracks in the rocks. And when the water freezes, it expands, which creates bigger cracks and breaks down the rock. And that's known as freeze-thaw.
Which is very similar to what destroys our roads in the winter.
Like potholes.
Yeah.
Exactly. It's just geology.
Yeah.
But then you have really hot climates, which definitely we won't have that in the UK. But in hot climates, there's a process known as exfoliation. And this doesn't mean your rocks are, become silky smooth. It just means that the temperatures on the surface of the rock create such pressure and stresses that make the rock peel almost like sunburnt skin. It like sheds almost. And you can see it in a lot of hot climates.
So are those the only types of weathering?
Well, no, these are all physical processes. So there's also chemical and biological. And so chemical is based on obviously chemical reactions like acid rainwater, whereas biological can be, trees, so plants that grow into the rocks, and the roots grow into the rocks and help break them apart. And all these grains and particles of the rocks tend to be carried away. And this is the next step of the rock cycle, which is transportation. And this can be down slopes, from mountains, in streams, by wind. And the particles, as they are transported, they smash together and they get broken down even more. And at the point at where this transportation mechanism, whether it's wind, water, gravity, can no longer transport the particles, then they get deposited. And they get deposited in a layer of sediment. And you see this in oceans or the bottom of riverbeds, sand dunes, along the coast as well, in deltas. So, like the Nile Delta in Egypt or Mississippi River Delta in the US, you get heaps of sand deposited right at the mouth of the river. And this process occurs on repeat, producing deposited layers upon layers, which creates weight and pressure on the layers below, which presses the particles together. And over time, you form solid rock, which leads to the next step of the rock cycle, which is burial and compaction. And you can see, like layers of a cake, these layers of rock of different deposition of sands and muds. Mm-hmm. And as you cut open this layer of cake, you can see the passing of time.
Great. And so that forms our sedimentary rocks, right?
Yeah, exactly. So sedimentary rocks are essentially made up of broken up pieces of other rocks or dead organisms or organic matter. So this can be made up of sands, muds, calcium carbonate, and some contain fossils and burrows of ancient life forms.
So you mentioned mud there. When I think of mud, I think too many people walking on the path in the park. Is that what we're talking about?
Well, technically yes, because we are talking about that similar sort of mud. But when you talk about geology, you're talking about grain size.
Okay.
And typically, you look at a sand. That ranges from a sand particle ranges from 2 millimeters to a 16th of a millimeter, and anything below a 16th of a millimeter, you have mud, and we define that as being very fine, or even more than very fine.
Whereas our sand would feel quite coarse, basically like sandpaper.
Well, yeah, exactly. Hence the name. But because they have different sizes, they tell a lot about the environments on which they're deposited. So larger grain sizes mean that the sedimentary rocks tend to have formed in higher energy environments, where there's lots of wind or water moving around, splashing around. So if you look at a sandstone, which could say marine or desert sands, you can see past sand dunes that have been preserved in the rock records that have moved based on the wind. And it's called cross-bedding. So you have these, if you look at a cliff face, you have these layers of sand that are laid down at different angles, and they alternate angles, like zigzagging on the cliff face. And water has a similar effect. I don't know if if you go walking at low tide, you see ripples on the surface of the sand. And this is sort of showing you the current or the wave direction. And this can be preserved in the rock record. And so you can see, preserved in the rock record, the direction the wind was blowing or the past currents of ancient oceans.
So our rocks are basically giving us insights into those ancient environments.
Yeah. And so for example, you have low energy environments where you have mudstone, and these tend to be posited where you've got not much movement, like lakes and deep oceans and lagoons. These are much calmer, so the fine particles can settle.
Okay, so what about limestones? We chatted briefly about them earlier.
Yeah, calcium carbonate. Well, yeah, so limestones, they contain lots of fossils or fossil fragments that collect on the seabed, and when they're buried, they harden. So coral reefs in time may become limestones, which represent these shallow marine environments. So lots of high energy, high levels of oxygen. And also, incidentally, they're called, you split them called calcium carbonate stones. And limestone sounds a bit of a, it's a bit of a stretch. It's not like a mudstone or a sandstone. It's a limestone. It's not, it's not like limes. It's a human thing. So we use limestones in construction for concrete. And when you burn calcium carbonate, you produce calcium oxide. You add a little bit of water to produce calcium hydroxide, because hydro means water in Greek. And calcium hydroxide is also known as lime. And it's used to this day for building works. And it dates back, and the use of lime has been dating back since ancient Egyptians when building the Great Pyramids.
Wow.
Incidentally, I learned a really good fact about the ancient, it's to do with the ancient pyramids, but really about Cleopatra. Okay. So did you know, have I told you this before?
I don't think
you haven't heard it yet.
Go for it.
Cleopatra was on Earth closer to the invention of the iPhone than she was to the building of the Great Pyramids.
No.
That's mad, isn't it?
That's crazy.
That is absolutely bonkers, because she was around. She was the last pharaoh of Egypt, I think, wasn't she? Okay. So, yeah, a few thousand years.
Wow.
Incredible.
It just blows your mind, doesn't it?
Yeah, it's mad. So, anyway, that's a bit of a segue. I think I've told you that before, but yeah. Anyway, so those are sedimentary rocks.
Yeah.
And they're essentially made up of broken pieces of other rocks and dead organisms. But as you go into the earth and you get buried deeper and deeper, things get hot.
Yeah, so we actually have something called the geothermal gradient. So on average, every kilometer you go down into the earth, you increase in temperature between 25 and 30 degrees. So when you bury your rocks deep enough, they melt to produce magma. And this magma rises back up through the crust, so kind of the upper layers of the earth, because it's more buoyant, it's a liquid. And as it rises, it can cool and harden. And as it hardens, it goes through a process known as crystallization, which means we are forming crystals of certain minerals. And that magma slowly becomes solid, and it cools to form igneous rocks like granites. And we see igneous rocks on the sea floor. We see them in lava from volcanoes, or, as I just said, in magma in the crust.
So, okay, great. So you have these granites and you have basalts, and these are all different igneous rocks. So how do you classify? What's the difference between those sort of rocks?
Yeah, so one of the big differences is the size of those crystals. So crystals that are forming from magma kind of under the surface, that end up forming rocks like granites, those crystals have time to grow because they're not cooling super fast. So you get quite large crystals. You get a texture called a phaneritic texture. Whereas your basalts, they're forming above the surface, or they can even form kind of as that lava moves into water. And so those crystals cool very, very quickly. We'd say they're quenched. And as they are quenched, they don't have time to grow nice big crystals, so they have very small crystals, and that would be an aphanitic texture.
Okay. I mean, I think someone I know has an obsidian crystal, which is just black.
Yeah, so this is the very extreme of that quenching process, where our crystals have had no time to form, or they haven't been able to form. So crystals need kind of nucleation points to form around, which might be kind of defects in the magma or the lava. And so obsidian is just a glass. So as I said earlier, it doesn't have any crystals. And obsidian can often form under the oceans, for example, when that molten rock is being extruded straight into water.
And it just cools super quick.
Yeah.
So obsidian's black, it's glassy, but I'm pretty sure that over time obsidian becomes crystalline because there's something called diffusion in this, like solid state diffusion.
Yeah, and it devitrifies. So basically turns from a glass and you start to actually form minerals.
So crystals form even though it's solid.
Yeah.
And you see this, because diffusion basically means the travelling of
movement
elements or within the crystal structure or whatever. I think it's pretty cool.
Yeah.
And so if sedimentary rocks are rocks that have been broken down and igneous is magma and lava that forms new rock, then you've got metamorphic rock in this rock cycle.
Yeah, so to complete the cycle. So metamorphic rocks basically form when we deform igneous and sedimentary rocks via heat and pressure. So we've already talked about the geothermal gradient increasing about 25 degrees per kilometre, and we get a couple of different types of metamorphism. So we've got regional and contact. So regional can be caused by things like plate tectonics, which cause large-scale kind of changes. And then contact metamorphism is more like when you get sort of a hot body of magma coming close to some other rocks, and that alters the original rock. And we would call that original rock the protolith. Proto, just kind of precursor, lith means rock. So that protolith could be an igneous or a sedimentary rock, or could even be another metamorphic rock. So our metamorphic rocks generally start to form above 200 degrees up to about 1100 degrees, just over 6.5 kilometers into the earth. And our pressures can range from between 3,000 bars to 50,000 bars. Now, maybe you can help put this into context a little bit.
Well, only because I did some reading on this the other day that I know that the bottom of the Marianas Trench, it's about 11 kilometres, so that's 7 miles, which is the deepest point of our planet. That reaches about 1,000 bars. Obviously, that's underwater, so it's not under the ground. But that's 1,000 bars, and that's huge pressure.
So we're talking about between sort of 3 and 10 times that. No, 3 and 50 times.
50 times, yeah.
3 and 50
Could be
times
10 times,
pressure.
but which is a huge amount. And then beyond those depths, you get between 100 miles or 160 kilometres into the ground. You have temperatures that range of greater than 1,000 degrees and pressures that are greater than 50,000 bars. And that's when you begin to form diamonds. Provided the rock is carbon rich, you form diamonds, which is known as the diamond stability zone.
Well, so we also have other types of metamorphic rocks, so they can form from sedimentary protoliths. So, for an example, would be a limestone. If that undergoes metamorphism, it can become marble, and a lot of kitchen counters are made of marble.
So so your kitchen counters are essentially made originally from the bones and shells of dead fish, which is pretty
A wonderful thought.
a wonderful thought. Pretty gross.
And as we get to the very extent of our temperatures, we can form a rock called a migmatite, which is basically where different minerals in our rock separate into lighter and darker bands. And this is like the point at which, if you go any higher, you're basically melting the rock. You're turning into igneous processes. So our migmatite kind of demarcates that boundary. And as I said, we've got all sorts of different processes that can create these rocks. So an example would be the mountain building process, where large slabs of the Earth's crust, the tectonic plates, are moving against each other, being uplifted into mountains. So an example today would be the Himalayas. Mount Everest is actually growing at a rate of about 4 millimeters per year as these plates, the Indian plate and the Eurasian plate, kind of smash into each other.
That's actually frustrating for anyone who's going up to the Himalayas. So like, if I walked up Mount Everest today, and you literally followed me up, if I got there and you followed me and you hovered and waited, I would be the highest guy on Earth. And then at that moment, as soon as I left the summit, and you walked up, then you'd be slightly higher.
Yeah.
But yeah, that's so frustrating. That's so annoying.
But you know, it's these places where we have these huge pressures that are creating our metamorphic rocks. And so in our metamorphic rocks, we can overprint, we can change, or even wipe out previous layering. So you were talking about sedimentary rocks, where you get those layers laid down, and actually we get new kind of textures forming in our metamorphic rocks that can wipe out those previous textures.
Essentially, if you're imagining two plates smashing against each other, it's like a car crash.
Yeah.
And the crumple zone is the mountains.
Yeah.
But the cars are continually crashing into each other.
Yeah.
Like they keep revving into each other over, like very slowly over time. I mean, just stop, guys. Like,
and then all these rocks, they get weathered down again, and we're back to the beginning, forming our sedimentary rocks.
Yeah. So those are our rock cycles in a nutshell. So we've got the igneous rocks that form from volcanoes and magma from the mantle, sedimentary rocks that form from debris of other rocks and living matter, and then your metamorphic rocks, which are a result of basically deforming and smashing up all the other rocks. Yeah. And that's about it, actually. That's the rock cycle. That's probably a good time to end, yeah. Thanks for joining me.
Thanks, Jack.
I hope everyone's enjoyed episode 1, and join us next time because we'll be talking about a chosen topic. Goodbye.